Welcome back to the Python programming tutorial series for climate mathematics theory and applications. In this video, we will continue to cover Chapter 3, Basic Statistical Methods, more specifically, looking at parameter estimates and the corresponding errors. Let's begin with some confidence interval simulation. Let us start off by setting our true mean and our true standard deviation. Our true mean for this example is going to be mu equals 14. Our true standard deviation is going to be sig equals 0.3. And we are going to be working with a sample size of n equals 50. Now let's define variables d, lower limb, and upper limb. We are going to be defining d equaling to 1.96 times sig divided by n to the power of 1/2. This is going to be our critical value for our confidence interval simulation. Our lower limit is going to be mu minus d, and our upper limit is going to be mu plus d. The number of simulations that we're going to be running is going to be k-sim, and we're going to run 10,000 simulations. Within our simulations, we are going to count how many times our random variable is within our lower limit and our upper limit. We are going to be counting how many times this happens with a simulation counter, namely k equals 0. Now let us start into our for loop. We're going to set up an empty array, namely x bar. Then we are going to set up our for loop for I in range of k-sim. So we are going to be ranging from 0 to 10,000 in our for loop. We are going to let x equal the numpy package mean method on a numpy random normal sample with mean equal to mu, sigma equal to sig, and a sample size of n. So every single time that this for loop is run, x will get redefined based off of the mean of a new random normal sample. We are going to append our x that we just defined in the highlighted code to our empty array x bar. So once our for loop is done running 10,000 times, x bar will have 10,000 means in it. Within our for loop, we do want a condition on our simulation counter. So we will do that by setting an if statement. If x is greater than our lower limit and less than our upper limit, then we will count 1 onto our simulation counter. This allows us to see the raw number about how many times our x, which is the mean of our normal random sample, is going to be within our confidence interval. Once that code is run, we can wrap it with some pretty print statements in order to get the results that we want to appear. Our simulation counter counted 9,499 times that x was between our lower limit and our upper limit out of the total number of simulations, which was 10,000. This is approximately 95% of our simulation was within our bounds we were looking at. Our lower CI was 13.92 and our upper CI was 14.08. In conclusion, out of 10,000 samples, roughly 9,500 of those samples had a mean that was in our bounds of our lower CI to our upper CI. Next, we will be doing a confidence interval simulation, but we will be assessing it visually using a histogram. We need to set our random seed first using that NumPy random package. We're going to use our seed method with some random seed number. This just resets our random module, so we are not adding to the random module that we used before. We are going to use 51 bins. So this tells us that our histogram is going to have 51 different blocks in it. Now we are going to go into creating our actual histogram, setting up our figure using the matplotlib subplots method. Then we are actually going to be inputting our data for our histogram. We are going to let n bins and patches equaling our matplotlib histogram of our x bar with our number of bins specified. The highlighted code allows us to see our histogram of our x bar means that we collected in the previous block. Our histogram is going to have a face color of blue, and we have an alpha value of 0.5. Next, we're going to label our histogram appropriately with title, Y label, and X label. Lastly, before we show our plot, we do just want to add a little bit of extra information that will get printed with our plot. We do want to note that our 95% confidence interval is between 13.92 and 14.08. So once we run this block of code, we will get this histogram out. We have 51 rectangles making up this histogram, dictated by the number of bins. We do have our print statement up in our top, so we do know that we can expect 95% of our sample to be within these limits. Next, we are going to go into plotting confidence intervals and their tail probabilities. We are going to use a special import statement for this example, so it will be discussed before going into the example itself. We're going to be accessing that matplotlib package. Within our matplotlib package, we are going to go into the patches module. From the patches module, we are going to import the function polygon. Because we imported polygon in this fashion, we do not need to precede our polygon function with any module or package name. Let's begin our example by setting mu and sigma. Roughly, mu equals 0 and sigma equals 1. We're going to create a normal probability function which follows the normal PDF. We are going to define it as int g of x, and we are going to return this arithmetic. This arithmetic that is highlighted does follow the normal probability function. We are going to set our desired quantities. We have a underscore and b underscore as 3, -3. Regular a and b as -1.96 and 1.96. And then our integral limits will be a1 and b1, which is -1.50 and 1.50 respectively. Next, we are going to set up a uniformly distributed number line between -3 and 3. This uniformly distributed number line will be called x. Then we will be setting y equaling to our function evaluated on x. Next, we're going to go up into setting up our figure. We're going to let fig and x equal that plt.subplots. Then we are going to plot x and y in black with a line width of 1. We are going to set the y limit with our bottom equaling to 0. So this is just going to line up the lowest y limit with the 0 unit. Now we need to go into making our desired shaded regions. We are going to be setting up uniformly distributed sequences ix underscore, ix, and ix1, all with the different parameters of the desired quantities. A underscore, B underscore is -3 to 3. A to B is going to be -1.96 to 1.96, and A1 to B1 is -1.50 to 1.50. Now we're going to use our integrating function on these variables that we just made. We're going to name them appropriately so we know which ones match up. Y underscore is going to be our normal probability function integrated on ix underscore. Iy is going to be our normal probability function integrated on interval ix, and ix1 is going to be our normal probability function evaluated on ix1. Next, we are going to be creating some desired vertical separations in our plot. We are going to have verts underscore equaling to the list comprehension of A underscore, comma 0. We are going to be using our star zip function in order to zip up values in between ix underscore and ixy. We are going to end our verts underscore array with a tuple of b underscore comma 0. These three lines right here correspond with the height, width, and end point of the vertical separations that we want. This will become more clear when we are looking directly at the plot. We are going to be creating desired polygons in order to shade the vertical separations differently. We are going to do poly underscore, poly, and poly1, just mimicking the format of our shaded region, our integrated function, and our vertical separations. We're going to be using that polygon function that we imported at the beginning of this block. We're going to be using our polygon function on the desired verts quantities. Our verts underscore is going to have a face color red and an edge color black. Our regular verts quantity is going to have a face color light blue and an edge color black. And lastly, our verts1 quantity will have a face color of white and an edge color of black. Now we are going to be adding these polygon patches to our plot. We are going to be using that by accessing the add patch function that is in the matplot library. We are going to be adding the poly underscore patch. We are going to be adding the poly patch and the poly 1 patch as we created above. Now we are going to be adding the appropriate text that we want. All of these text functions take x variable followed by y variable as their first parameters, dictating the start position that you want your text to lay at. So this half of a plus b is just letting Python know that we want the following text to be directly in the middle of our plot. But we do want it to have a height of 0.24 in our plot. The third parameter for our text function takes the actual text that you want to be displayed on your plot. The text function has many other parameters such as horizontal alignment, vertical alignment, font size, and font weight. You can dictate these things as you see fit. You can read more information about these parameters in the documentation of the text function. We are going to be adding the rest of this text to our plot as well. We have a few different SE marks, and we also have a X bar mark, which will indicate where our mean of our distribution is. Next, I will be creating desired arrows in order to just indicate some important things that we will be able to see in our plot. I'm going to be making an arrow with an arrow function from that matplot library. You can look at the documentation of the arrow function in order to find out what these parameter order go in. We're going to be putting some text on top of that arrow indicating what our arrow is pointing at. Our arrow will be pointing at a probability of 0.025. We do want this positioned directly next to our arrow, so this position will coincide with our arrow. Last but not least, we are going to label our figure. Y label is going to be probability density. X label will be true mean as a random variable, and our title. We are going to set our X ticks as our A1, B1, and B parameters that we defined above. And we are going to set these tick labels as empty tick labels. So we get the tick marks to appear, but we do not want them to be labeled. Lastly, wrapping that block with PLT show, we do get this confidence intervals and confidence levels plot to appear. What made our polygons appear was that polygon function. We do have different areas that are shaded, indicating the different confidence levels and confidence intervals. We can see that our X bar is directly in the middle of our distribution. This is absolutely correct and informative, telling us that our sample mean has the highest probability density. The red tail ends both have a probability of 0.025, indicating that everything within the red shaded areas is truly a 95% confidence interval on our sample. This concludes the estimate and error section of Chapter 3, Basic Statistical Methods. In the next video, we will wrap up Chapter 3 with a video focusing on confidence intervals and statistical inference.